Welcome back, everyone. In this video, we're going to review a little bit of what we learned already about periodic table and effective nuclear charge, and then we'll look at how there are trends within effective nuclear charge that affect other periodic properties. We're going to focus in this video on the atomic radius. So let's review a little bit about properties of elements. And it turns out that we can use quantum numbers and electron configurations to understand the periodic properties within the periodic table. So the properties that we are most concerned about, that we're most interested in, are the radii of elements, whether in their neutral atomic form or their ionic form, the ionization energy of an element, in other words, the energy that's required to pull off an electron from the element. We're also interested in looking at electron affinity, which is the energy involved in adding an electron to an element. And then finally, reactivity. Ultimately, reactivity as a whole is what we care about in terms of chemistry. And the quantum numbers, principal quantum number and the L quantum number, the size and the shape of orbitals are going to affect the periodic properties. The atomic number also affects periodic properties, and so we're going to explore how this is the case. Let's remind ourselves a little bit about the organization of the periodic table before we do so. So we've referred to the various regions of the periodic table as blocks. We have the S block, the P block, the D block, and the F block, and those correspond to the orbitals S, P, D, and F. We've also looked at the periodic table in terms of its periods. Those are the rows, and these period numbers also correspond to the principal quantum number n. So for the main group elements, if we look at the third row in the S block, then that's telling us we're looking at the 3s orbitals. If we look at the fifth row in the P block, then we're looking at the 5p orbitals. As a reminder, with the D block, for a given row, the shell value there is actually n minus 1. So if we're in the fourth row here, then this would be n minus 1 or 4 minus 1d. So this is 3d, and then this is 4d, etc. The F block is similar, but it is n minus 2. So this corresponds to the 6th and the 7th rows, and so this would be 6 minus 2 F, or the 4F subshell, and then this would be the 5F subshell. You need to be familiar with which elements, which regions that the left-hand side of the periodic table are metals, and then the right-hand side are nonmetals, and then where our staircase of metalloids is. You also need to be aware that the terminology we use for columns, those are called groups or families. And then also that elements within the same family are going to have similar properties. So for example, elements that are in main group number 4 are going to behave similarly, but they will behave differently from main group number 7. However, the elements of main group number 7, the halogens, they behave similarly to each other. Let's now review what we learned already about the effective nuclear charge. This is the nuclear charge that's experienced by a given electron based upon its position. We use the analogy of sitting around a campfire, saying that if someone is sitting in front of you blocking you from the fire, that you feel an effectively lower amount of heat that's given off. Similarly, this electron that's being shielded by the core electrons has a lower effective nuclear charge. And we can calculate that through this equation. So the effective nuclear charge of this element is equal to the number of protons. Let's just say that there's 3 protons in this element. So that would be 3 minus the screening constant, which is the number of core electrons. So we count up here, we have 2 core electrons, 3 minus 2, that's equal to 1. Okay? Now if we wanted to find the effective nuclear charge of these electrons, we take the number of protons minus the number of electrons that are screening them. There are none in between them and the nucleus. And electrons within the same shell do not screen each other. So that's 3 minus 0, or 3. And so we can see that there is a higher effective nuclear charge for the core electrons versus the outer electrons. And this is going to be very important to understanding periodic properties. Let's talk now about the periodic property of the effective nuclear charge. This figure here comes from the ebook, and it shows the approximated value of effective nuclear charge in orange as calculated here using this equation. The blue uses much more sophisticated calculations using computers and accounting for the electron-electron repulsion within a shell to calculate the effective nuclear charge. And so we can see that there's relatively good agreement, especially early on, but then as we get higher in our proton number, that the discrepancy is larger. However, there are a few trends that hold true both for the approximated values and for the actual calculated values. The first trend that you need to be familiar with is what happens as we go from left to right across a periodic table, across a row. So let's take a look at the actual data here. As we go from left to right, we're going along one of these diagonal lines. We can see that the effective nuclear charge increases as we go across the row. Now, what's the reason for that? Well, remember, when we go from left to right, what we're doing is we are adding in protons, neutrons, and electrons. And there is one more proton in carbon than there is in boron, and there's also one more electron. Now, remember what we said, though. We know the protons go into the nucleus, and the electrons are going on our outer shell. So if we take a look at boron, it has 5 total electrons. It has 2 electrons in the core, and then we're adding electrons on the outside as we think about a new from boron to carbon. So boron, the outer electrons are being shielded by these core electrons. If we now look at carbon, carbon has 6 protons, 6 electrons. But the electrons that we've put in the outer shell are not being shielded any more than they were than was the case for boron. So when we look at the Z effective, the number of protons is going up, but the core electrons is staying the same. Therefore, while this number goes up, this stays the same, and so our effective nuclear charge goes up. The next thing to realize is that we have a very sharp drop-off in effective nuclear charge. Once we get to the end, we've filled up a shell and we drop down. Now, the reason for that is because once we've added in all of these electrons into what is our outer shell, and we start a new layer, all of those electrons that were the valence are now also part of the core. So now when we look at sodium, sodium now has 10 core electrons, whereas neon only has 2 core electrons. And so that increase in core electrons shields the outer electron and greatly reduces the effective nuclear charge. The last trend you need to realize is that the effective nuclear charge has a very slight increase as we go down a column. We can see here, if we look at elements within the same family, that there's a very slight increase in that. We're not going to get into the details about that, and what we can see is that is not being predicted by the approximated values here. So the two that you really need to pay attention to are these first two. Now, we want to talk about how does the effective nuclear charge affect the radius of an element. in order to talk about that, let's first define the radius. So when we look at the radius of an atom, the radius of the atom is the distance from the nucleus to the edge of the electron cloud, to where those outermost orbitals are. Okay. Now, however, when we talk about once we start looking at bonding and molecules, we can see that those elements are going to get closer to each other. And so we have a bonding radius that is smaller than the atomic radii of the free colliding atom. So, how does the atomic radius vary throughout the periodic table? Well, one thing that we want to understand is that the radius increases as we move down a column. Remember that as we go down a column, we're increasing the number of shells. Because the number of shells is increasing, the element must be getting larger. Think of it like you're putting on more layers. You first put on a t-shirt, and then a sweater, and then a coat. As you put on those layers, the radius, the size gets larger. And so it's simply because the number of shells we have increases, the elements get larger. Those electrons, as we put in those outer shells, they're farther away from the nucleus. Now, atomic radius also decreases as we move from left to right across the row. Now, why might that be? Well, remember, we talked about how the Z effective will increase as we go from left to right because we're increasing the number of protons without increasing the number of screening electrons. So why does the atomic radius decrease as we go from left to right? Those two things are related to each other. Remember, the effective nuclear charge is essentially how strongly those electrons feel they are pulled to the center of the nucleus. And so elements, as we go across the periodic table, they are having a larger and larger pull on them into the nucleus. We can quantify this by using the effective nuclear charge, the Bohr radius, and the shell number. Now, you will not actually need to make any calculations with this, but what we see then is the two things that we already mentioned, that the radius is going to increase as the shell increases, but it decreases as the effective nuclear charge increases. Again, why is this? Remember when we looked at Coulomb's law, we talked about how the energy of interaction is proportional to the product of the charges over the distance. Well, if we look at this in terms of our effective nuclear charge and the electron, as the effective nuclear charge gets larger, the energy attracting the nucleus and the electron is more attractive, and it pulls those electrons closer to the nucleus. There's higher attraction, therefore the electrons are pulled in closer, and the atom itself is smaller. Now, we'll notice here that there are some exceptions to that. Typically within the transition metals, or the F block, the lanthanides and actinides, those will go against the trends for reasons that go above and beyond what we want to talk about for Chem 110. So what's most important is that you realize the overall trend, that the radius decreases from left to right, and that's due to the effective nuclear charge, but that the radius of elements gets larger as we increase the N value, because we're increasing the number of shells. All right, let's try a practice problem. Order the following according to increasing atomic radius. How would we do this? Well, we want to look at their locations on the periodic table. Based on their locations, we can predict their relative sizes. We know that the atomic radius decreases as we go from left to right, and it increases as we go from top to bottom. So if we wanted to put them in, if we want to make a comparison, then we know that magnesium is going to be larger than chlorine. Okay? Comparing magnesium and barium, we know that barium is going to be larger than magnesium because it's beneath it. And then cesium to barium, we know, again, barium is going to be smaller than cesium because of the difference in the effective nuclear charge. So we've now been able to make a comparison between each set of elements. We want to put them in increasing atomic radius, so we want the smallest on the left. Our smallest is chlorine, followed by magnesium, followed by barium, and then cesium. And indeed, if you were to look up the values, you would see that our prediction holds true. That's it for this video. Thanks for watching. Have a great day.